Well, I have to say it's a little difficult to follow a talk about how not to write bad code because now I'm suddenly very self-conscious about all the code that I've written for this. So thank you, Mikhail. So today I want to talk about a troublesome subject for, I think, many developers, but also many humans in general, which is the idea of time. And you've heard Jameson talk briefly about some of the stuff that I do, but regardless of what you do, I imagine that regardless of what company you work at or what kind of code you write or what your profession is, you probably intersect with the idea of time in some way. And if you can't, I'd love to understand what your job is because I'd love to not have to care about that anymore. So this talk is fundamentally a talk about assumptions and how they can often lead us astray in complex domains, especially when those domains don't seem complex or they seem like intuitive or accessible to everyone. It's easy for us to make mistakes or slip up. So here's, for example, a snippet of Python. This is inviting the user to consider whether the object allocated by A is the same as the object allocated by B. And you may wonder whether this is true for a given value. So A and B have the same value, but are they the same object? And it turns out that the answer is true. Yes, these are, in fact, the same object for Python. And if you repeat the exercise for 22 instead of 2, you also get that they are the same object. And if you do it for 222, you also get that they are the same object. And when you try this exercise for 2,222, they're not the same object anymore. Why did that happen? Seems surprising. And it leads to sad kittens. And the reason it happens in Python is that's a specific implementation of Python called CPython. And for performance reasons, CPython caches small integer values in the range -5 to +256 so that they're all singletons. But the second you get outside of that range, they're not singletons anymore. You're making a new object for every instantiation of a specific value. Maybe you've wondered at some point in your life while you're in the bathroom or something and you don't have any reading material and you've exhausted all the ingredients on your shampoo bottle and you're wondering, how do I compute a leap year? How do I know if this year is a leap year? So given some year Y, how do I know if it's a leap year? And the mental model that I think most people have about this is, well, if you take the year and you divide it by 4, and there's no remainder, then that's a leap year. So 2016, for example, would be a leap year because you can divide 2016 by 4 with no remainder, and you get 0. So that would be a leap year, which is correct. 2016 is a leap year. But it turns out that 2000 and 1900 and 2100, those are all multiples of 100. And it turns out that, for example, 2100 will not be a leap year. So the next century interval, 2100, will not be a leap year. But then it turns out that 2000 was a leap year. So the rule is that it has to be divisible by 4, and if it's divisible by 100, then it's not a leap year, unless that year that's divisible by 100 is also divisible by 400, and then it is a leap year again. So that's a really complicated rule that I think most people don't carry around in their heads as a conception of how that works. And it turns out that there's a lot of rules about time and our specific representations of time that violate some of the sort of natural assumptions we might want to make, leading to more sad kittens. And sometimes the assumptions we make in our software aren't even really about code. They're just software that's encoded some kind of sociocultural assumption about the way the world worked. So for example, this is a picture, the two women in the center. The woman on the left is a woman named Hillary Goodridge. She's a US citizen who lived in a state called Massachusetts. And in 2003, the Massachusetts State Supreme Court decided a case called Goodridge versus Massachusetts Department of Health, and that was the case that legalized same-sex marriage for the first time in the US at the state level. And I was involved with a sort of a re-engineering that needed to happen because many of the county and town systems that recorded marriage licenses had databases that did that, and all of a sudden they needed to be updated. And you saw a lot of people write schemas that looked like this, where you have marriages between one man and one woman, and that's it. All of those databases have to be updated. And that, that's a lot of nice extra consulting dollars, but it's not so great in terms of encoding our sociocultural assumptions into software. So this is something that's not even reflective of a physical reality the way that like time might be considered to be a part of physical reality. So if we can't even get like the sociocultural stuff right, that doesn't really bode well for the like physics objective stuff that doesn't have any or has fewer sorts of those issues. And even if that's not the only problem that this schema has. There's lots of other hidden problems that are lurking here. For example, what happens when people get divorced? How do you represent that in the schema? You can't really. You'd have to null out the issue date, perhaps, so then you'd lose the record of when they were married in the first place. So it's very, very problematic for a number of reasons. So back to time. What is time? So when we think of time, what are we talking about? What are the ideas that that sort of shape what time is? Is it one big thing? Is it a collection of little tiny things? And there have been a lot of philosophical debates, and this is by no means a settled question whatsoever. And it's a perennial sort of discussion in philosophy circles about what is time. And in the background is a painting by Salvador Dali named "The Persistence of Memory." And one of the characteristics that people often describe about this painting is just the sort of mutable aspect of time, the subjective nature of it. And when we think about time, I don't know if everyone thinks about it as being subjective, and that seems like it could be a thorny topic. So what have philosophers in the past said? So you may recognize these two gentlemen who are both dead. One on the left is Isaac Newton, and the one on the right is Immanuel Kant. And Newton said, his sort of theory about this was that time is really independent of any individual person. My perception of time is the same as your perception of time. It's not, the idea of 3 seconds is an objective reality that we can't disagree. Reasonable people cannot disagree about what 3 seconds means. And Immanuel Kant said, well, no, that's not really true. Time is not an empirical idea. Time is like color. So it reflects a physical reality, but it's a perceptual reality. Like my idea of green is different than your idea of green, maybe different than somebody else's idea of green. And although that's based on a physical representation of the wavelengths of light, it doesn't mean that our perceptions are the same. Then you have JavaScript sort of entering the picture about 500 years later with a very different idea of what time is and a very specific representation of what time means. So this is today's date and roughly this time in JavaScript. And that's a really different perception of what time is from these two philosophers. And and they might be horrified to discover that that's what we've reduced time to. And these represent really different philosophies of seeing time. So who's right? Which of these approaches is the correct one? Are they all correct? Are 2 out of the 3 right? Are none of them right? And there's a different perspective we haven't considered. So are we mapping the right thing, or is this another case of bad assumptions? And I think for this talk, just for the sake of proceeding onward so we don't all get stuck in philosophical analysis paralysis, we'll say that time is what separates events from one another. So just like space is what separates me from Jameson or someone else in the audience, time is what separates this sentence from the one that follows, from the one that follows after that, and so on. In the same way, if you were inviting a friend to dinner, you would sort of give them four coordinates, right? You would say, meet me at this location, that's 3 dimensions, and then meet me at this time, which is a 4th dimension, right? So you need all 4 coordinates in order to have a meeting, right? So think about that the next time you're scheduling meetings in your calendaring system. You're actually doing 4D math. So if we try to develop a domain model of time to sort of explore this idea, to explore the representations that might be possible and which ones are appropriate, we first have to sort of go back to basics, go back to first principles, and probably, and the word that we use to describe a systematic representation of time is called a calendar. And if we'd like to have a systematic representation, we need to understand what goes into that calendar. And unfortunately, the early proto-humans did not have Google, so they could not ask a question of how do I invent a calendar? And so what did they do? How did they arrive at a notion of time and the passing of time? Well, when you look at early civilizations and their representations of time and calendars specifically, you see things, you see certain thematic elements occur over and over again. And one of the big thematic elements is that of cycles, of something that starts, ends, and resumes again over and over and over again without end. And there's something, I think there's something to that. The cycle idea is interesting because it means that if we can count the number of times that something happens, for example, a cycle, then we can sort of measure the passage of time by indicating the number of cycles that have occurred of that thing. So for an early human, what are some of the ways that they could represent those things? They might say, remember the last time they ate something, and then count the number of times they had eaten, right? So that might be one thing. Or they could observe the number of times they saw a particular bird, and then if they see that bird again, that will be another chalk on the cave wall. Or they could measure, say, something a little bit longer, like the passing of seasons. If they see the leaves fall from a bunch of trees at the same time, maybe that's their conception of autumn and so on. So longer periods and so on. But the idea we're trying to get to here is that it's useful to consider these cycles, the idea of an event occurring over and over again, and then incrementing sort of a counter that represents the number of times that that event has happened. And when we do that, that's called a period. So when you have a period, you have an event, and then that event recurring at some point in the future. And the length of that time is called a period. So this is the initial skeleton of our domain model. We don't have a lot in this toolbox right now. We just have periods. So let's start with that and see where we go. So on the next iteration of our toolbox, we want to start taking advantage of the world around us. So we live on a planet, and that planet rotates. And because it rotates, that means that the side of the planet that faces the sun is different at different times. And because it rotates in a relatively consistent way, that means that we can track the number of cycles equal to the sun going down and then coming up again. That's one period. We call that a day. So that's the solar cycle, the sun going behind the horizon and then back up, and then reappearing from the other side a day later. Now, it doesn't work if you're at certain latitudes, like Norway would be one of them, for parts of Norway anyway. So, this is already subjective. It's already dependent on where you are in the world. But this is probably the best early humans could do. The next sort of thing we can take advantage of is the fact that as we're on this planet, we may notice that there's sort of this round object in the sky that changes shape over time, and that round object is the moon. And because the moon is locked in tidal concert with the Earth, meaning that the same side of the moon physically faces the Earth all the time, it's just that the side that's lit is different, which is why you get different phases of the moon. But the physical side that faces the Earth is the same. So if you take a picture of the moon, no matter what, where you are on Earth or where you take that picture from, you'll be getting more or less the same side of the moon facing you. And one cycle, it takes the moon about a month of our current calendar to go around the Earth. So we call that a lunation. So our toolbox is getting a little bit more sophisticated now. We have the idea of a day and a lunation. But if we can survive for longer periods of time, we will be able to see that over longer and longer periods of time, we don't just have days. We notice that the sun goes to a different point in the sky each day. So the highest the sun gets in the sky from the same location on Earth is different at different points of the year. But after a certain amount of time, which we'll call a year, the sun goes back to the same point in the sky that it was a year ago. So that's 1 year. So if today is June 2nd, and I look at the highest point in the sky from this location where the sun is, and I come back a year from now, the sun should still be roughly at that point in the sky. If I come back a week from now, the sun will be at a different point in the sky at its highest point. So our toolbox is getting more sophisticated. We have some ideas of periods that we can use to draw on to make our calendar. And so our idea of what the kind of things we can measure with time is getting more sophisticated. Now, at this point, we can count days, we can count lunations, we can count years, and so on. But it's subjective in the sense that this is objective. It's hard to disagree about the number of times that something has occurred once we've agreed on what that definition of a day is. So if we agree on what a day is, we can simply count, well, We've seen 7 days, 8 days, 9 days, and so on. But what we might disagree about is what is that point in the middle of a day that we don't yet have a division for? So we don't know how to divide the day up any more finely than a day. So if that's true, if we want to like indicate that point to each other, we might say something like, well, that's day 182.25, day 182 and a quarter. Well, it's not very helpful because that's pretty that's pretty subjective in terms of what that means. And how we talk about that to each other might be different. So modern time folks like us might describe that as being 6 o'clock in the morning. But someone who is an ancient Sumerian might have called that the 5th night hour. They divided the day up into 10 periods of night and 10 periods of day. But the difference was, or the length of each such period was different because the nights were different lengths than the days. So they had different divisions for different times of day. So this is, until we can agree on each specific subdivision, we're not going to be able to agree on what time it actually is. So our toolbox needs to get a little bit more sophisticated. And specifically, we have to think about what it means to have a calendar. So a calendar, when you get down to it, in the modern reckoning anyway, it's a mapping, it's a function that takes a day number and returns a date. So, for example, in the Gregorian calendar, which is the one we're all used to, the day is a number that counts up from a specific date, which is January 1st, 4713 BCE. And then every day since then has been an increment of 1 since day 1. So today happens to be day 2,456,973. And we write that date, or most of us write that date, as June 2nd, 2017 in the Common Era. But this is arbitrary, right? You can have any function that maps any day integer to any date string. So if you were in the Game of Thrones universe, you might have a totally different representation of that. Instead of being June 2nd, it might be, the fifth moon past in a specific solar cycle or something. So fictional universes or other representations of time on Earth might agree about the day but disagree about the date. So the date is just the string that represents the way of describing the day to other people. So we can add this to our toolbox now, this idea of a function that takes a day and returns a date. But you can see that already we're getting really, we're getting kind of fuzzy at this point. The stuff that's on the left is more objective. Everybody can kind of agree on what a day is or what a lunation is or what a year is. Not everybody agrees that the Gregorian calendar is the best way to represent things. Why are there 12 months? Why aren't there 17 months or 3 or 2 or 9, right? Why are there 30 days in some months and 28 in others, but sometimes 29 and so on? So there's a lot more subjectivity around the selection of the calendar. And then even worse, there's a lot of subjectivity around what time it actually is. So I'm going to invite everyone to just breach conference etiquette for a second and pull out your cell phone or look at your watch. And on the count of 3, I'm going to ask you to just yell at maximum volume what time you currently think it is. So 1, 2, 3. All right, okay, cool. So I heard some people say the hour and the minute. I think I heard a couple of people say the AM part. I don't think I heard anybody say seconds, but it was hard to see 500 people. But you can see that just the question of what time is it, we disagree about how much detail I need to provide you to answer that question. So, you can say, well, it's 6:30 at some moment in time, but you could also get really, really specific about how, if I ask you what time it is, do I need to know what millisecond it is? Probably not if we're talking, but maybe if we're talking about calibrating a atomic clock or a telescope or something like that. And this gives rise to another idea of moments, which is, if you imagine the spectrum of time, all possible times that could exist, and we focus on, say, 6:30 a.m. this morning, and I say, it's 6:30, what does that mean? Well, that doesn't mean a point. When people say it's 6:30, I think people think of it's a point, this moment is 6:30. But actually, 6:30, the statement, it's 6:30, is true for a range of values, not a point in time. All of the times in between 6:30 and 6:31, it's correct to say that it's 6:30. And depending on who you are, it might even be correct to say that it's 6:30 when it's 6:33 or 6:27, especially if you're frequently late to things like I am. So, and it's not helpful necessarily to get more specific. If we use seconds here, all we're doing is narrowing the interval that we're talking about. We're not reducing it to a point. We're just shrinking the width of the interval. So we have a problem, which is that moments, or our sort of canonical description of time, is ambiguous. It's not just that it's an interval, it's also that that interval is ambiguous, because the statement, it's 6:30, does not contain enough information all by itself to resolve to a specific moment in time. So for example, it's 6:30 could refer to 6:30 a.m. today or 6:30 p.m. today. Not if you're on a 24-hour clock, but for those of us who aren't on a 24-hour clock, it might be true. And it doesn't help just to say it's 6:30, because we have to identify all the pieces that are ambiguous about that statement and then resolve that ambiguity. And so the moments denoted by the statement 6:30 there's more than one of them per day. And again, it doesn't help to be, if we look at multiple days, we see that pattern recurring over and over. And it doesn't help if we get more specific. If we go from 6:30 and then provide the seconds, all we're doing is shrinking the interval. We're not providing a disambiguation on the statement. Now, the reason that I don't blow up when people tell me it's 6:30, I'm like, what are you talking about? I have no idea what time it is. You need to be super specific, or else I won't be able to function as a human being. The reason that works is because I'm not a computer, and I can take facts about the context we're talking about and incorporate them into our shared understanding of time. But computers can't do that. They need specificity, not just granularity about the time. So it's not sufficient to say it's 4 o'clock. You have to say it's 4 o'clock p.m. on a Thursday, May 14th, 2015, in the Gregorian calendar, and so on, right? So if we take that statement and we say, okay, well, this certainly seems specific enough. Surely this will be enough for JavaScript. You would be sadly mistaken. Because if you give the computer this information, if you ask JavaScript, hey, give me a date that represents that time I just told you about, you get this extra bit that we never specified. What is this? What's this part that's hanging off the end here? It says GMT negative 0400 parentheses EDT. I didn't say anything about that. That's not part of my time system. And more confusingly, can other things go there? If I didn't specify that, who gets to decide what that thing is? And if that's part of our shared temporal representation, then do we have a problem, because we're not speaking the same language? So it seems like there's a really big missing part of this time domain model, and what is that? How do we get unique representations of time so that there's no ambiguity about what we're talking about when we say that it's 6:30? So to get unique times, we have to resolve a few problems with our domain model. First, humans generally want times to correspond to the solar day, meaning that in AM, we want times to be when the sun is up. So if I say that it's 10 a.m., I want the sun to be out. I don't want it to be dark. So I want to pick a representation of time such that morning times are in the morning and evening times are in the evening. Well, that's really difficult because we live on a round planet, despite what a certain segment of YouTube might tell you. That planet, because it's round, it's spherical, not everybody is going to experience morning at the same moment in time. So it's impossible to have it. It's already impossible to have a time system in which we both agree that it's 6:30 a.m., but it's morning for one person on one side of the earth and morning for another person on the other side of the earth. That's impossible. You can't have it both ways. So the gentleman that resolved this was a guy named Charles Dowd, who was a seminary teacher, and he proposed the idea of time zones to a bunch of US railway operators. And we liked the idea so much that this was legally adopted in the United States in 1883. And he was frustrated because he would take the train from one state to another and go hundreds of miles, and he'd have to constantly be readjusting his clock to synchronize with the station's local idea of what time it was. So you could drive 20 miles and have a totally different idea of what time it was, because everything was set from the local clock and not from any shared understanding of time. So he said, well, that's stupid. We should just have a shared understanding of what time is. There should be a common offset so that everybody who wants it to be morning at a given time, they can just we can all just agree on some universal time and then offset by that time so that we wind up in AM or PM. So for example, I live in Charlottesville, Virginia, and I have a friend who lives in Maryland, New South Wales, and Australia. And when I say, hey, call me when it's 9 a.m. for you, he's going to call me when it's the morning for him. And if he says, call me when it's 9 a.m. for you, I'll be calling him in my morning. But those are two different times. We just have local understandings of what 9 a.m. means in our specific time. And that's achievable because we all have a reference time, which is called UTC, and then we offset by a given number of hours from UTC to arrive at a consistent local time. All right, that seems like it resolves one of the problems, but here's another problem. What if we're not using the same calendar? What if I'm in Charlottesville, Virginia, in the US using the Gregorian calendar, but my friend in Beijing is using the Han civil calendar, which is a totally different system, a totally different idea of months and dates and so on. Or what if you're using a religious calendar? There are many, many different religions with many, many different calendars that celebrate specific feast days and so on. So very, very complicated to resolve that. So the only way to resolve that is we all just have to agree for the sake of trade or commerce or shared understanding to use the same calendar. But we're going to have to remember when we switched calendars to that same shared calendar. Otherwise, we'll all get our previous dates wrong from before the switch. So in 1582, everybody in Europe pretty much switched to the Gregorian calendar from the Julian calendar. But if you ask now, hey, what happened on October 5th, 1582 in the Gregorian calendar, or in the Gregorian calendar, there is no October 5th, 1582. That will cause an error when you try to resolve that in a specific time library. Here's another problem. Our idea of what offset it should be changes over the course of the year. Maybe you've heard of something called daylight savings time, which is terrible. So we have different ideas of what it means to have a specific offset over time. So in Charlottesville, we have UTC -5 in the winter, UTC -4 in the summer. My friend in Maryland, New South Wales has UTC +10 and UTC +11. But winter and summer actually mean different things in Australia than in the US. And we may disagree about when we're going to set our offsets differently. So in Maryland, New South Wales, they jump forward and back in October and April. But in Charlottesville, we do it in November and March. And in the past, even worse, we've changed our minds about when that should happen, right? So in Charlottesville, it was true that it was the first Sunday in November and the second Sunday in March, except through 1917, 1942, through 1944, specific windows in 1947 and 1948, et cetera, et cetera. Maryland, New South Wales, same thing, but a completely different set of times. And even more confusingly, some of the times that you might want to talk about don't actually exist in my local time zone. So if I say 2:30 a.m. US Pacific time, Sunday, March 9th, 2014, seems like a perfectly normal, reasonable time. If you ask a library, please get me the Pacific time zone, and then say, please convert that date to a time, it doesn't exist. There is no UTC time that maps to that time. And that's because that occurs within a daylight savings jump. So you go from 2 a.m. to 3 a.m. on that morning. There is no intermediate time of 2:30 a.m., so that's not a valid time. And conversely, you have the opposite problem when you go backwards in time for daylight savings, right? If you go as soon as the clock ticks over to 2 a.m. the first time on a fallback daylight savings time day, then you are experiencing all the times from 1 a.m. to 2 a.m. once. You go back an hour and you experience all of them again in local time. So that means that when you ask a computer, hey, what time is it for that local time, it can't give you an answer because there's more than one possible answer. So you have to tell it how to resolve that ambiguity somehow. There's more than one reference time that maps to that time. So clearly there was something missing in our domain model. And we have to introduce a few more pieces. So the first is we have to introduce the idea of a reference time, the Charles Dowd idea. We're all going to agree on a common clock. Second is we have to have some idea of local time and then an offset between reference time and local time that we'll maintain so that it's always morning for us. And then we have to remember how those offsets came to be and what they were. So just like a calendar is a mapping of days to date strings, a time zone is a mapping of a reference point in time somewhere in that spectrum to an offset that should occur from the reference time. So at this moment in time, I can tell you what the offset should be from UTC for any particular place on Earth. And that's because we all have time zones. And again, because the time zones change over time, we'll have to remember what they were at different points in time. So that sounds complicated. Let's make a database. Fortunately, someone has already done this for us. A wonderful organization called the Internet Assigned Numbers Authority maintains something called the TZ database, a time zone database of every single time zone that anyone has ever come up with. And you need one time zone for every list of historical offsets you might have had. So every country that ever decided what time it was at a specific moment in time, that's got to be recorded somewhere, or else you won't have a correct representation of time for that specific country or city or whatever. And the TZ data looks like this. It's got all these rules and time zone things, and you can see things like if you look at a specific rule, it tells you what window of time this rule is active for and when it happens and what the offset should be. And here's when America switched to Charles Dowd's system. And that LMT means local mean time. That's the setting your clock by the railway station. I mean, they said, well, after November 18th, 1883, we're not using local mean time anymore. That was stupid. And then the rest is regular time zones. Now, because time zones are permanent, that means that every single time that someone changed their mind about what time it should be, that was another distinct time zone. So as you can probably imagine, there are a lot of time zones. There aren't like 24. So just in one state in the US, there are 23 time zones representing different cities' ideas of what time it was at historical offsets. So Indiana has a lot of trouble making up its mind. So how do we solve this? Well, fortunately, there are libraries. So JavaScript has Moment.js, Java has JodaTime, .NET has a port called NodaTime, Ruby has something called Active Support, which is not very good in terms of representing times. Python has PyTZ and Arrow, which are a little bit better. But the point is that we need something to kind of represent this time zone aspect. So we need something there, and that's usually it's TZ data, and it's a library that's interacting with TZ data to get you the right rules and process everything correctly. So if we want to work with times in our programming language, it's really important to think about intention and how we represent that. So if I say to you, hey, wake me up at 6 a.m. tomorrow, or if I say to you, this meeting that we're having is on the 29th of every month, or I want to go to the gym 3 times a week. So think about the first one. If I say, wake me up at 6 a.m., I'm from Charlottesville, Virginia, I just flew to Norway, do you think I want to be woken up at 6 a.m. Charlottesville time or 6 a.m. Oslo time, right? So if I want to make Web Rebels, I want 6 a.m. local time, Oslo time. But if I set my clock when I was over in the US and my calendaring system said, yeah, sure, I'll convert that to universal time for you and store that, well, that wasn't what I wanted. I wanted the local time I happen to be in when the alarm goes off. Or if I say this call is on the 29th of every month, do you think that means that the meeting is canceled in Februaries where it's not a leap year? Or if I say that I want to go to the gym 3 times a week, should that be 3 precisely equally spaced moments in time? So if I divide the week if I have 7 days in the week, do I take 2.6 days apart is when I'm going to go to the gym? So I'm going to the gym at 4:30 a.m. on one day and 6:15 p.m. on the next day. So the problem is the date math doesn't express intention. So we're missing the last piece of our domain model. And to resolve that, we need something called a duration. And a duration is a precise, objective representation of time. It's a precise, a precise, objective representation of time. So if I say 1 month, and I mean 30 days, and I mean 30 days with 24 hours in them, and each hour has 60 minutes, and each minute has 60 seconds, and I can tell you that 1 month is precisely 2,592,000 seconds. And if I say a period, though, and I mean 1 month, that could mean lots of different things. If I say 1 month, that could mean 1 month. 1 calendar month, like January is the same as February. That could mean 30 days. That's like the average or the median of the length of a month. It could mean 28 days if I'm talking about February. It could mean 4 weeks if I mean the number of full calendar weeks in a given month. It could mean 5 weeks if I mean the number of full calendar weeks in which at least one starts on Sunday. It could mean 6 weeks if I mean a calendar month in which any day starts on any part of the week, right? So there's a subjectivity associated with periods that's not associated with durations. And that's really important for working with libraries. In Moment.js, for example, if I say, hey, let's talk about January 30th, 2014, All right, so I've got that date. And then I say, I want to go 2 months in the future from January 30th, 2014. Well, I get March 28th, 2014. Why'd that happen? Even more weirdly, if I start from January 30th again, and then I say add 2 months, so not add 1 month twice, but add 2 months once, I get a different answer. I get March 30th, not March 28th. So these operations were not associative. How did that happen? Well, it happened because when you added the first month, you went from January 30th to February 28th. Then you add another month, and you went from February 28th to March 28th, versus going from January 30th to March 30th in one step. Subjective period versus objective duration. So we have to match our usage of time libraries to our intentions. Here's another example. If I say October 1st, October 2nd, and November 1st, November 2nd, and November 3rd, I'm already tripping up over JavaScript's use of months being indexed by 0 instead of by 1, so that 10 represents November and not October, right? Because you start from 0, so 0 is January, 1 is February, et cetera. Anyway, so if I have November 1st, November 2nd, November 3rd, 2014, November 2nd, 2014 happened to be a DST transition. And if I say, what's the difference in second, or in milliseconds in this case, between those two dates, I get, well, it's 90 million milliseconds, or 90,000 seconds between November 3rd and November 2nd, but it's 86,400 seconds between November 2nd and November 1st. So it seems like we have a disagreement about what one day is, and that's because we used periods instead of duration. If we instead say, well, no, I want to know about days, I want to know about I want to use that as the specific representation. So I say, OK, well, then November 3rd is 1 day after November 2nd, and November 2nd is 1 day after November 1st. So if we want to talk about days, which is a period and not a duration, then we can get the answer we might expect, a consistent notation of days. The last thing I want to say is we need to be really careful about the assumptions our library is making. Here's the same situation, November 1st, November 2nd, November 3rd. Well, on the first day, we have November 1st at 1 o'clock in the morning. Second day, we have just before that at 12:59 a.m. And then the third day, we have 12:59 a.m. again. So if we say periods, yeah, we get 1 day. They're 1 day apart. That makes sense. But if we say, what's the difference between November 3rd and November 2nd, we get 1 day. But if we say, what's the difference between November 3rd and November 1st, we also get 1 day. Well, that's not what we wanted. We wanted an answer like 2 days, that November 3rd is 2 days after November 1st. And that's because we used periods instead of duration. And in Moment.js, the assumption is that if you don't have a full window of that period, we have a little bit less than 1 day between November 2nd and November 1st. It won't round that up to being a second day. So our library made an assumption that maybe wasn't what we wanted it to be true. It might be useful in other situations, but it wasn't in this one. So that represents our whole domain model. We have a full representation of time. And at this point, we can sort of go forth into the world. I know Isaac Newton and Immanuel Kant would be proud of us. So would our JavaScript forebears, because we sort of reconciled this idea that, well, time is subjective. It's also objective. And yeah, you can represent times in JavaScript with new date, parentheses, a bunch of parameters. They're just different slices of the same idea of time, of a human representation of what that idea is. And so time is complicated. It's multifaceted because we're complicated and multifaceted. We have really different ideas about how calendars should be written and how time should be tracked. And because we have to keep track of that complexity somewhere, well, it wound up in software, right? But if you find yourself interacting with these systems or designing them or using a time library, you should probably not reinvent the wheel. You should probably take advantage of the domain models that already exist. Don't add 2 dates together by yourself. Use a library to do that. Use something that has canonicalized the idea of that domain model into a library so that we have a shared understanding of time versus fragmenting it further. And so if you're going to interact with time, be consistent for the sake of your fellow humans, because nobody wants more sad kittens. Thanks very much, and have a wonderful conference.
Thank you. My first question is, have you considered becoming the dictator of the earth to just abolish, like, no one gets daylight savings time. There's one time zone. It's 4 a.m. when you go to bed. Who cares? Like, I don't know. That's my reaction to hearing all this.
I mean, I'll be optimistic about that happening when we can agree on like metric. But maybe we can get past that first. We can agree on like time zones, and I feel like that's probably easier to solve because there's like only 2 systems instead of thousands, right? Like there's thousands of time zones. So there's really there's imperial and metric. So if we could just maybe have the U.S. move a little bit closer to that side of the scale, we'd be better off. Yeah,
I think everyone would be willing to agree as long as it was like 9 a.m. when the sun rose, wherever they lived. Like,
exactly.
Oops, now you have time zones again. The slide with Kant and Newton and then JavaScript, that was a big hit. A lot of people liked that. Those 2 people are dead. JavaScript is not dead, so I guess it's right. It won.
Right, to the victor go the spoils. So,
So is there, one of the themes I got out of this was that this idea of time that we don't think that much about is kind of horrifyingly complex underneath. Are there other things that are like that we're just blissfully unaware of, that secretly there's just this massive...
Yeah, I mean, I think there's so many things, especially when it comes to software, right? Like what we're doing when we write software systems is fundamentally we're encoding something about the world into a software system. So some fact, some behavior, some outcome that we'd like to be true, we are encoding that into a software system. And so that can lead to a lot of mapping of bad sociocultural assumptions into our system. So I don't know if anyone remembers when Google Plus, the social network that Google rolled out a few years ago, they initially had a real names only policy, and they abolished that pretty quickly because it turns out it's very difficult to tell whether a name is a real name or not. And I was rejected from Google Plus because they didn't think that John Feminella was a real name. But so I was like, that's fine. It's a pretty weird name. And also, I don't care about being on Google Plus that much. But then I got mad because later I found out that there was a thoracic surgeon, a guy who opens up your abdomen and like pokes around in there to fix your pancreas or whatever. There was a thoracic surgeon on Google Plus named Dr. Loki Sky Lizard. And I was like, how are you going to tell me that John Feminella is not a real name, but you accepted Loki? I mean, that was his real name, Loki Sky Lizard. And I was like, that's an awesome name, but like, if you didn't know anything about it, you would think it was fake, right?
Yeah.
So that's just like one example that I can think of. But even going back to time for a second, like, all like Moment.js and all the time libraries we have, they only kind of work because we're here on Earth and we don't have to deal with things like relativity very much, right? The second we start talking about like, sending rocket ships to Mars and going like fractions of the speed of light, all of this will break all over again. And we'll just find out all of the bad assumptions that have been made about what it means when 1 second passes here on Earth doesn't mean that 1 second passed on the rocket ship, right? So I look forward to the Y2K equivalent of whatever hitting some reasonable fraction of light speed is.
Yeah, the relativity plugin for Moment.js.
Exactly.
Someone can write that. A question from the audience was, how do you deal with things like age limits in multiple time zones in this chaos, right? If you have to be 18 to vote or to drink or something like that. Or to get into a club.
Age limits in multiple time zones? I hope that I never have to deal with a system where I need to think about both age limits and time zones and like reconcile them in some way.
Okay.
So oh, you mean like verify if someone is 18 at a given moment in time?
Yeah.
I mean, I think that should be, if you know the person, if you know the date on which they were born and you know the calendar in which that date is being recorded, then in theory, you should have an objective measure of whether they are 18 in a given time zone or not. Now, what may not be written down anywhere is like the rule about when are you 18. Like, for example, in some states in the US, if in the US, you can't drink until you're 21 years of age. And so you're usually in university at that point. And if you take your ID to the bar, what they're checking is today's calendar date is 21 years after after the date in which you were born. So that means that if you were born on, say, February 28th, 21 years ago, and today is February 28th, then that's fine. But what if you were born on February 29th, and then today is March 1st? Is that okay? What if it's February 29th? But there's been several leap years since then. So is that like, can you go actually earlier than February 28th because that would still be 21 years old? Like,
Yeah.
So those rules I don't think are written down anywhere necessarily about how old one has to be. So that kind of stuff could get tricky for sure.
That's why it's traditional to bring your birth certificate with when you go to a bar in the United States. It's American culture facts for you. One more question was about the Internet's Assigned Numbers Association.
Yes.
Do those people just like party like rock stars and do a lot of cocaine? That's what I imagine their life is like.
Yeah, I mean, you know that those standards bodies are just like out of control, right?
Yeah.
So I mean, I don't know if I'd be pretty happy if I like figured out how to wrangle time zones into this like canonical format so that everyone could use them. I'd be really happy about that. So I probably would party.
Or maybe you would drink to forget.
But then maybe they wouldn't know how to take my ID at the bar because they wouldn't be able to tell if I was 21 or not without some serious date math. So.
Yeah. Well, thank you so much for your talk. That was fascinating.
Thanks,
John.
Thanks, everybody.
So we